Now we shall discuss about a 1D heat conduction problem that takes place in a plane wall. And plane wall means a wall that has no curvature. It is a flat wall type of thing, like the wall of a room. And we take a wall which has a internal heat generation, and the wall is under steady state. So we consider a steady state 1D heat conduction problem in a plane wall with internal heat generation, volumetric heat generation.
জিরো হয়ে যাবে তো টাইম ডিপেন্ডেন্স হয় না বলে ডান
Yes,
দিকেরটা। হুম।
ডান দিকে জিরো হবে, many more things will be zero. Now, when we take 1D heat conduction, that means the heat is flowing in one direction only. And let's say that direction is this direction, and we call it X. There is a direction and along which the thickness is small compared to the height and depth of the wall. So what happens is that if there is a temperature difference across this thickness of the wall, because of the temperature difference, the heat will start to flow, and more so it will flow because the thickness being very small, there is a concept called resistance to the flow of heat, that also will be very small. So because of those things, heat will flow mostly along X, and there will be very little flow of heat along Y, the height direction, and Z, the depth direction. And because there will be no heat flow along Y or negligible heat flow along Y and Z, so that will be also characterized by a negligible temperature gradient along Y and Z, and there will be a considerable temperature gradient along X. And so because at any Y the temperature gradient is zero, ultimately del to T del Y2 will be zero, and similarly at any Z, because del T del Z will be equal to zero, so ultimately del to T del Z square also will be zero, and because of steady state nature of the problem, this term also will be zero. So the equation will simplify to d to t dx square plus g dot by k is equal to 0. But this g dot stands for the uniform volumetric heat generation, and k is the thermal conductivity of the medium that constitutes the wall. And one thing that we very frequently make a mistake of being not very concerned about this thing is that when t is no more a function of y, z and time, and t is only a function of x, that is t varies only along x, then del to t del x square should be replaced by d to t dx square. So this equation 1, which is a more generalized equation, except the fact that this k is uniform, that is why we can write it outside these differentials. So this is an equation that is valid for a uniform thermal conductivity, and that too it is independent of the direction. So this is valid for a wall having isotropic thermal conductivity of constant magnitude. And from there, applying the particular cases of simplicity, that is del t del y 0, del t del z 0, del t del time 0. So these terms will cancel out, del 2t del y square, del 2t del z square, and del t del time. This will become 0, and the equation will simplify to d 2t dx square plus g dot by k equal to 0. So the simplified equation I think we have shown over here. This is the simplified equation d to t dx square plus g dot by k equal to 0, and this is valid inside the wall excluding the boundaries. That is why this is valid between 0 x equal to 0 and L, and not valid on the wall, which on not valid on the outer surfaces of the wall, that is at x equal to 0 and x equal to L. And at x equal to 0 and x equal to L, there are two more conditions which are required to be given to solve this equation. They are called the boundary conditions. The boundary conditions are T equal to T1, that is the left side of the wall is maintained at a constant temperature T1 at x equal to 0, and the right side of the wall, which is at x equal to L, that is maintained at a constant temperature again, that is T2. And if T1 is greater than T2, then heat will flow from the T1 temperature surface towards the T2 temperature surface. That means it will flow along positive direction of x. And if we integrate this thing, these are called boundary condition. And this being a second order equation, you require two boundary condition to evaluate the constant of integration C1 and C2. So if you integrate this thing, this stands for, if we integrate, you get dt dx equal to minus g dot by kx. That is, if you bring it first of all on the right hand side and integrate, then dt dx becomes equal to minus g dot by k into x plus a constant of integration. And if you further integrate, then what you get is a temperature variation along x given by T is equal to minus g dot by k x square by 2. So it is g dot by 2k into x square plus C1x plus another constant of integration C2. Now this C1 and C2, so long as we don't supply any boundary condition, we cannot solve the values of C1 and C2. What remains is a general kind of equation that is valid for all problems having the similar conductivity, similar g dot value, identical thickness. But so long as we don't specify the temperatures on x equal to 0 and x equal to L, these does not specify any specific problem. It remains a general description of a problem that may be valid for all walls having internal heat generation, having the same conductivity, having the same thickness. So these boundary conditions, by applying which we can find out the values of C1 C2 so that the solution becomes unique, they are also called the condition of uniqueness. They are also called the conditions of uniqueness, because then the problem becomes unique and that is distinct from any other general problem. So what we can do is that we can apply this boundary condition t equal to t1 at x equal to 0. So when we put t equal to t1, x equal to 0, then c2 becomes equal to t1. So it becomes t equal to minus g dot by 2k x square plus c1x plus c2, because c2 becomes equal to t2. And then if we bring everything on the other side, and we can find out c1 will be equal to t minus t2 by x equal to L my plus g dot by 2k. What happens is that it becomes equal to L, because is L square and there is a L, so it becomes L. So your C2 becomes equal to T dot by 2k L plus T2 minus T1. This is this is equal to x equal to, at x equal to L, this becomes equal to T2, and this is T1, so it becomes T2 minus T1 by L, because from this it comes that L. So this is how we find out the values of C1 and C2. I'm just stating certain things, but then I'll give further explanation on those things, what we are doing, what extra we can interpret out of these results. So if we put the values of C1 and C2, the complete solution for T comes out as this thing, that is T equal to minus G dot by 2k x square plus C1 value is this is a C1, that is equal to G dot by 2k into L plus T2 minus T1 by L, that is a C1 value into x plus C2 has been already obtained as T1. Now up to this it is straightforward mathematics actually. But there are a lot of things to be seen through this equation. These equations are something that actually describe certain physical phenomena. And we would like to develop certain acumen or a habit of seeing through this equation. We can see a number of things that we'll discuss first of all. That first of all, why at all we find out this thing? To find out the temperature distribution, how does it help us? As you as you are aware now that the subject is heat transfer, and the objective of this subject is to find out the rate of heat transfer, not temperature distribution in general. The primary intention, the primary objective of the study of this subject is to find out the rate of heat transfer in a given situation. So why at all we find out this thing, temperature distribution? Because as I have said, is that we can find out once we know the temperature distribution, then we can find out the temperature gradient, and then we can find out the heat flux across a surface through the use of Fourier's law of heat conduction. So to find out the heat flux through the wall at any surface, because if we want to find out the heat transfer through this surface of the wall, the heat transfer through this surface of the wall, we must know what is the heat flux that is valid over this surface. The heat flux that is valid over this surface, if we know, then we will be able to find out the heat transfer rate as an integrated value of that heat flux over the surface area. Now, if the heat flux is constant over the entire surface, that means if it is constant or uniform over the entire value of y and z that constitutes this wall has certain height. We can say for this wall, y varies between 0 to h. And if the depth of the wall is w, then the z varies on this wall, the z varies between z equal to 0 to w, and y varies between 0 to h. So, and what we see is that on this entire surface, the heat flux, if we now examine, what will be the nature of heat flux? Will it vary over the surface? The heat flux, will it vary over the surface? If you see, the temperature distribution doesn't have anything to do with y and z. So whatever be the heat flux, which we can obtain by taking a derivative of this thing, the derivative of temperature is equal to minus g dot by k into x plus c1. And as we have seen that the value of c1 has some constant value. It is a constant. So del t del x is equal to some function of x plus a constant. So del t del x, dt dx does not change along y and z. And how do we get the heat flux? If we simply multiply minus k with the temperature gradient at a point, we get the heat flux at that point in the direction along which we are taking the temperature derivative. Now, because we are finding out the temperature derivative along x, so if we multiply that with minus k, we get the heat flux along x. So what we get is that the heat flux along x, now if we put the value of the coordinate of the wall at that coordinate of the wall, what is the coordinate of the wall? The wall has a coordinate of x equal to 0. So if you put this thing, then what you get is that dt dx on the left hand side will be equal to simply the value of c1. Okay, dt dx will be equal to, because at x on the left hand side of the wall, x equal to 0. So dt dx on the left hand side of the wall will be a constant that is given by this thing. So if you multiply this with minus k, what you get is k into t1 minus t2 by L minus g dot into L by 2, because we have multiplied this with minus k. So your heat flux becomes a simple constant that does not change along y and z on the left hand side of the wall. So the heat flux is uniform over the entire surface of the wall, that left hand surface. So to find out the heat transfer rate, we don't require to integrate even. The heat transfer rate will be simply that heat flux which is uniform throughout the wall multiplied by the surface area of the wall, that is given by H into W. So what we see is that to find out the heat transfer rate, we require to know the heat flux, and to find out the heat flux, we require to know the temperature gradient. That's why we solve for the temperature distribution. Because until unless we know how the temperature varies along x, we cannot find out the temperature gradient along x. So that is to find out the heat transfer rate, we have to know the heat flux. To know the heat flux, we require to know the temperature gradient, and to know the temperature gradient, we have to find out the solution for temperature. That is why in every heat transfer problem, most of the heat transfer problem will be mostly dealing with what is the nature of variation of T along with x, y, z. Then only we will be able to find out those heat flux and subsequently the heat transfer rate. Now, There are other things that we'll discuss about this solution. Another thing that we see is that in this case, the temperature gradient is a function of x. It is varying with x, and that indicates that the heat flux also will change with x, because heat flux is simply temperature gradient multiplied by minus of k. Because temperature gradient is changing with x, so the heat flux also will change with x. And when the gradient changes with x, that means the nature of variation of T is not a linear one. If the variation is a linear one, then the gradient will be constant all through the span of value of x. But here dTdx is a function of x means T is not a function, T is not a linear one. Precisely, this if the gradient is a function of x in a sense that is proportional to x, then the T will be a quadratic equation of x. This is something more that we will compare with other situation. Now, what we have done here is that once we find out the temperature, we can we can also find out the heat the temperature gradient, that is equal to minus g dot by k into x plus c1. So c1 value, if we put dTdx equal to minus g dot by k into x, this is a c1 value plus c1. So what will be the heat flux at x equal to 0? That is the left side of the wall. Heat flux at the left side of the wall where x equal to 0. So the heat flux at q equal to x equal to 0 will be equal to minus k into dt dx at x equal to 0. If you multiply this with minus k, and minus becomes plus, and k cancels, x equal to 0, the whole value cancels. And again, if you multiply this with minus k, then it becomes minus g dot L by 2. And here if you multiply with minus k, it becomes equal to k into T1 minus T2 by L. So it becomes k into T1 minus T2 by L minus g dot by 2L. G dot by 2L. Now, what we can say about the sign of this quantity on the left hand side, because it is something minus something. Now, this something is a positive quantity. This k is a positive quantity, L is a thickness is a positive quantity, and we have assumed that T1 is greater than T2. We have imposed the temperature in such a way that the left hand side wall is hotter than the right hand side wall. So T1 minus T2, the temperature on the left hand side wall minus the temperature on the right side wall. This difference is positive because T1 is greater than T2. So this is a positive quantity, and also because of this heat generation, G dot is a positive, L is a positive quantity. So it is some positive quantity minus another positive quantity. Now this difference may be less than 0 if this part is, the second term is greater than the first term. It may be greater than 0 if the first term is greater than this thing. It may be equal to 0 when if first term is exactly equal to the second term. So there are every possibility that the heat flux may be negative, the heat flux may be negative less than 0, may be equal to 0, or may be positive. So when heat flux is negative, that means what? That means the heat is coming in the negative direction, coming out in the negative direction. So heat flux negative means the heat is coming out of the wall. The heat flux positive means it will be going inside the wall. And when it is equal to 0, then heat will neither come out of the wall nor it will go inside the wall. So a very strange situation will occur when this term becomes equal to this term. Then what will happen is that even if the left wall is hotter than the right hand side wall, no heat will either come inside the wall or no heat will come out of the wall. So the left side of the wall will behave like an ideal adiabatic surface, a surface across which there is no heat flow, even though there is a temperature difference between the two surfaces of the wall. The left side is hotter than the right hand side. So what we expect is that normally it will flow from the left side wall to the right side wall. But because of the presence of this term, it may make the heat flux to be negative when heat will come out. It will be positive when heat will go along x, that is, it will go enter into the wall. and when these two becomes equal, the first term becomes equal to the second term, then there is no heat flow across the wall, left side of the wall. So the left side of the wall will behave like an ideal adiabatic surface. It is not an assumption, it will happen like that. On the other hand, if we see the heat flux on the right side of the wall, what will be the heat flux on the right side of the wall? Then you have to evaluate this Q at x equal to L. That will be again minus K into dt dx at x equal to L. So what is the value of dt dx at x equal to L? With a minus, it becomes equal to minus and minus will cancel. So it will become G dot into L, because K and K will cancel. There is a minus K dt dx, and there is in dt dx also there is a divided by K. So it will become plus G dot into L. Then here it will become minus G dot into L by 2. So it becomes ultimately, because first term is plus G dot into L, second term is minus G dot into L by 2. So ultimately it will become G dot into L by 2. It becomes G dot into L by 2. And what happens to the last term? Because of presence of minus K, it becomes K into T1 minus T2 by L. K into T1 minus T2 by L. So what we see, the heat flux on the right hand side of the wall, this will be some positive quantity plus another positive quantity. So it will be always unconditionally greater than 0, means it will be positive, means the heat will flow out of the wall in the positive x direction on the right hand side. The right hand side of the wall, the heat will come out along the positive x direction. So what will happen is that we take this problem, we consider this problem. What is the problem? That there is a wall, the thickness of the wall, and the heat flow is taking place only along x. So we are not concerned about the other two dimensions of the wall. There is the height and the depth. Only we are concerned about the thickness, because along that only the heat is flowing. And if the left surface of the wall is heated uniformly at a temperature T1, if the right surface of the wall is heated uniformly at a temperature T2, but the value of T2 is less than T1, then what will happen? From this, the heat will always come out along the positive x direction. We cannot say whether it will come out or it will go in or nothing will happen. As we have seen, there are different possibilities. The heat flux may be negative, so heat may come out in the negative direction, because x positive is here, and heat may flow in the positive direction, in which case the heat will come from outside to inside of the wall, or it may be that there is no heat flow across this thing, so heat neither comes out nor goes inside the wall. So three alternative possibilities are there so far as the x equal to 0 is concerned. But at x equal to L, it will always come out. That is so because of the nature of the problem that you have considered over here. Now, there is something more to be discussed about this thing, the results. Because once you find out the heat flux, then what will be your heat transfer rate from the left side of the wall? That will be simply the heat flux, which is a constant throughout the left side of the wall. It does not change along y. It is not a function of y. It is not a function of z. So that means that throughout the left side of the wall, at any point on the left side of the wall, the same heat flux prevails. So the heat transfer rate, the total rate of heat transfer on the entire surface area of the wall will be simply the heat flux multiplied by the area. If it were a function of y and z, then you had to integrate that heat flux. But because here heat flux is constant, even if you integrate, that constant will come out of the thing. It becomes integral of q dA. That becomes q integral of dA, because q is constant. The heat flux, the q is constant. So if you want to integrate, even if you integrate integral of q dA, because q is constant, it comes out. It becomes simply integral of dA. So it becomes equal to q into the area of the wall, that is given by height multiplied by the depth of the wall. It becomes this quantity into h, the height, into W, the depth of the wall. The whole thing into the surface area of the wall. Similarly, the heat transfer rate that takes place from the right hand side of the wall, that becomes equal to this into H into W, the surface area of the wall. Now, if we find out what is the net heat inflow into the wall, that is the heat coming out of the right hand side minus the heat that is going inside the left hand side. If you take this thing, then what happens? If you make a net heat flow into the wall or out of the wall, the net flow heat flow out of the wall is given by the heat flow out minus the heat flow in, as if from the left hand side wall the heat is coming in and the right hand side of the wall the heat is going out. So the net heat going out will be equal to this into area minus this into area. So if you do that thing, then what happens is that this part and this part, they will cancel out, and this part into L into A by 2. L into A means what? Means the volume of the wall. Because if we take the heat transfer rate, then you have to multiply this with the area. So if you multiply L into area, that becomes the volume of the wall. So it becomes G into V, G dot into V by 2. And here also, because you are subtracting this term from this term, so it is equal to G into L by 2 into area plus G dot into L by 2 into area. So ultimately it becomes G dot into V. What does it mean? What it means is that the it is the net rate of heat generation inside the volume, because this G dot stands for the rate of heat generation per unit volume. Multiply that with the volume of the wall, it gives you the what is the net rate of heat generation inside the wall, and that net rate of heat generation inside the wall is the thing that comes out of the wall, because heat cannot be generated. So where from it comes out? It comes out from the fact that whatever is being generated inside, that comes out of the wall. So the net heat that comes out under steady state, that will be equal to this G dot into V simply. There is further thing that we'll discuss on this is that this problem is actually, it is we can think of this problem as if it is made up of two problems. It is made up of two problems. So that thing is called something that we'll discuss, that we are going to discuss now. Suppose your temperature is the cause for this heat flow, and that temperature capital T, if we denote this as a summation of two different unknowns, T is the dependent variable, the unknown that we are trying to find out. And if I define this T as equal to two more unknowns equal to U plus V. Now, if we can think of this problem that we are considering, our problem is like this: d2t dx square plus g dot by k equal to 0 with a boundary condition given by t equal to t1 on the left hand side and t equal to t2 on the right hand side. Now we can think of this problem as if made up of two simplified problems. What are the two simplified problems? One problem is where you don't have any heat generation. There, this T, the problem on T is made up of two problems in terms of U and V. The U problem, this is the U problem where there is no internal heat generation. You have simply d2u dx square is equal to 0. And your boundary condition is T, this not T, U equal to T1, and on this side you have U equal to T2. Plus, there is another V problem which contains the heat generation term given by d2v dx square plus g dot by k equal to 0 with boundary condition, identical boundary condition v equal to 0 and d equal to 0. Now, if you add these two problems, then what happens? Then if you add these two, it becomes d2u dx square plus d2v dx square plus g dot by k equal to 0. Now, if you write this d2u dx square plus d2v dx square as equal to d2 dx square of u plus v. Then it becomes d2t dx square. And then there is the additional term, the heat generation, that is g dot by k. Now this way of splitting or adding to get the solution. Now if we do this thing, we can get a solution for this u. If we look at this problem in terms of v, we can get a solution for v. And what we can say is that the solution for t can be obtained by adding the solution for u plus the solution for v. So whatever solution for u we get, whatever solution for v we get, if we add these two, then what we get is the solution for t. This method of solution is known as the method of superposition. Now, when we can add or break this one problem, a complex problem, into two problems, is if the problem nature of the problem is a linear one. So, if we see this problem in terms of the differential problem that we are solving here, what is the problem? The problem is the union of the governing equation and the two boundary conditions. The governing equation along with the specification of the boundary condition that fully describes your problem. So the problem consists of specification of the governing equation and specifications for the boundary conditions. Now, if you see this governing equation has a term that contains the unknown the t to the power 1. So that is why this is a linear governing equation. And again, the boundary condition is given in terms of t equal to t to the power 1 equal to some constant, t to the power 1 equal to some constant. So that is why this problem is considered as a linear problem. There may be some problem where this linearity does not exist. For example, we think of the original thing where from this k came. This k came into this term because it was there ddx of k dt dx. Now ddx of k dt dx, actually k was connected to this, k was a product of this thing. Now when k becomes a function of temperature, then what happens? Then you can write that k in terms of some function of temperature. Then what happens is that this term gets connected to another thing that is connected to t. So it becomes t multiplied by t type of thing. So then the power of t to the power 1 does not exist. Then the power of t becomes more than 1, then it becomes a nonlinear problem. So if you have an equation where each term along with the coefficients, if the terms are having some t to the power 1 and the coefficients are constant, or if the coefficient is there, that is a power to t to the power 1 with something that is a constant. In essence, if there is some product of terms and such that the product becomes t to the power 1, other terms become t to the power 1, then you can call that problem as a linear problem. And if you have a linear problem, then you can use the method of superposition to get a solution to a complex problem by splitting the problem into two simplified problems and then get the solution of the two simplified problems, add those solutions to get the solution for the complex problem. That is how at times we solve a more complex problem by splitting the thing into two constituent parts. That method is mathematically called as a method of superposition, and we can use superposition for a linear problem, but we cannot use the method of superposition for a non-linear problem. When linear problem will be, when the problem will be linear, if the properties, the particular property that we consider over here, the conductivity is constant, then the problem becomes a, this becomes a constant, then it becomes linear in terms of t. But if the conductivity itself is a function of time, a temperature, then the thing becomes k into dt dx, something like d2t dx square plus dk dx into dt dx, something like that. So in that case, each of the terms will have t into some derivative of t, t into double derivative of t, something like that. Some constant double derivative of t, something like that. In that case, the problem becomes t into t type of thing, then it becomes a nonlinear problem. And there we cannot apply the method of superposition. Now let us discuss one more thing out of this complex problem is that, before we go into that, let us further see what will be the final solution like. And to know the final solution like that, if we take this problem and if you solve, then what you get, what is as a solution, then it will be the solution will be E equal to T1 plus T2 minus T1 by L into X. You can solve this thing, you can put the boundary conditions with U equal to T1 and E equal to T2. What you will get is a solution for U equal to T1 plus T2 minus T1 minus T2, sorry, E equal to T1 plus T2 minus T1 by L into X. Can you see this thing, or it is very, because it is hazy somewhat? Can you see the
No, so
solution?
it's
Yes,
visible, sir, visible.
yes,
Visible.
clearly the question.
Now again, this describes a lot of things. If you see, there is a solution that U, the solution for U is linear in terms of X. So when the solution is linear in terms of X, then it means that the gradient of that solution is a constant. When the variable is varying linearly, that means the gradient to that variable is constant. That means the gradient value is constant. Now, this is one thing that will come to later on. And for the second part of the solution problem, d2v dx plus g dot by k, you solve this thing. What you get is a parabolic equation given by g dot l square by 2k into x by l minus x square by l square. And when you get the solution for t, as I said, this t is nothing but summation of u plus v. So the solution for t will be equal to the solution for u plus solution for v. So it will be simply addition of this part and which you get mathematically as this part. This we have done already. Graphically, if you see, how do we get the solution for t? The graphical representation of that thing, that is, if we add on this line at any x, whatever the height of this thing, if we go on adding at each and every x, if we go on adding the value for v as addition, you get a series of points, and if you join those points, we get a curve like this. So that is the final solution for the temperature distribution. Again, this has a lot of things. Let me take a 5-minute break and then I'll discuss. Okay, just I am feeling
Okay, okay.
it tires me actually to talk
Okay, sir, no problem, sir.
now. Let me tell about certain other aspect of these solutions. Everybody is there, or somebody has left like that.
Yes, sir. Yes, sir.
হ্যাঁ স্যার আমরা আছি
Now,
স্যার, অসুবিধা নেই কোনো।
না সেটা বলছি কেউ হয়তো 5 মিনিট বলেছিলাম, somebody may go out. Now this is the solution for u. What is u? The u is some kind of temperature, because we have taken t, the temperature is equal to summation of two more problem or two more function, two more independent variable u and v. So temperature cannot be equal to pressure plus volume kind of thing. So whatever t represents, the same thing u should also represent, v also should represent that thing. So if t represents temperature, then u also should represent V also should represent temperature. That is something called as a principle of dimensional homogeneity, that T has a dimension and each term on the left hand side and right hand side of this equation that represents some physical quantity, they all will have the same dimension. The dimensionally they will be homogeneous. The equation should be homogeneous, so that each term will represent the same quantity. It may be temperature, so every term will represent temperature. If it is pressure, then every term should represent pressure, like that. So if T represents temperature, that means U also should represent temperature and V also should represent temperature. If you examine this solution, U is equal to T1, that represents temperature, plus a difference of temperature is also temperature, into length by length. So it becomes independent of length. So U represent a temperature plus temperature, that becomes as a whole a temperature. So dimensionally is quite compatible. If you look into the solution for V, there also this x by L is a dimensionless quantity, is just a number. X square by L square is also a number, a dimensionless number. And let us see the unit of this thing, G dot L square by K, because 2 is also a number. What is the unit of G dot? That is equal to watt per meter cube, called the volumetric rate of heat generation. Rate of heat generation is W, watt. Rate of heat generation is watt, per unit volume is watt per meter cube. So G dot has a unit of watt per meter cube. And if you multiply that with meter square, L square, so it becomes watt per meter cube into meter square. It becomes watt per meter. And what is there on the denominator? The unit of K is, you should try to remember this thing, it is watt per meter Kelvin. So on the numerator we have watt per meter, and on the denominator you have watt per meter Kelvin. So effectively it becomes equal to Kelvin. So this also represents, Kelvin means it represents a temperature, and this is a very standard way to represent some kind of a temperature. Not a temperature, it becomes a temperature difference type of thing. Because what is happening is that if you have a problem of this is the problem, then what does it represent? It represents that there is a wall, inside that there is a continuous rate of heat generation, and the two walls they are maintained at some constant temperature, identical temperature. Then what will happen, because the wall has the two surfaces both are maintained at ideal temperature V equal to 0, V equal to 0, then what will happen, identical amount of heat will come out from this wall and this wall. Then the heat which is being generated, it will try to come out. Otherwise what will happen, the temperature of the body will tend to go up. Now the problem that we are discussing is a steady state problem. That means the temperature at any point inside this volume does not change with time. Why at all temperature changes with time, and when does it change, is to represent a increasing energy. Now if the body is under steady state, that means there is no change of temperature with time. That means the energy content of any point inside this volume does not change with time. So how it will be possible? Is the only way is that whatever is the internal generation of heat, that has to come out by the same magnitude. So whatever heat is generated, what is the rate of heat generation? Is equal to G dot into V. What is the net rate of heat generation? Because G dot is the rate of heat generation per unit volume, and if that is constant over the entire volume, then the rate of heat generation over the total volume will be equal to G dot into V, where V is the volume of this wall given by L into H into W. So G dot into V is the heat generation, and out of that G dot into V, G dot into V by 2 will come out through this, G dot into V dot G dot into V by 2 will come out through this. So half of the heat which is generated inside the wall will come out through this, will come out through this. And because from both the sides the heat comes out by equal magnitude, so the heat flux on the left hand side should be equal to the heat flux on the right hand side. Because the heat flux is same on the left hand side and right hand side, so the temperature gradient also must be same on the left hand side and right hand side by magnitude. But because heat flux on the left hand wall there is negative, and heat flux on the right hand side wall, that is positive. So what will happen? Heat flux on the left hand side is negative, so the dTdx will be positive, because heat flux and dTdx, they will be opposite in sign. That is why you require to multiply with minus k. Heat flux equal to minus k into dTdx. That means if dTdx is negative, then heat flux will be positive. If dTdx is positive, then heat flux will be negative. So when heat flux is negative, that means your dTdx will be positive. And what does it mean? It will have a rising temperature. As you move along x, the temperature should rise. And on the right hand side, what happens? The heat flux is positive. That means the temperature gradient will be negative. And what we mean by negative temperature gradient? That is when you increase the value of x, the temperature decreases. When you go for increased value of x, your temperature decreases. So here there will be a rising temperature, and here there will be a falling temperature. Moreover, if you look at the central line of this volume, if you draw an imaginary line through the center, then what direction of the heat will flow across that line? The heat will flow across that line in which direction? It will neither flow in the right hand direction nor it will flow in the left hand direction, because there can be bias in this problem, because this problem is symmetric about
Thermal symmetry, yes, thermal symmetry.
so it is having a symmetricity along the midline of this wall. So whatever happens in the left hand side, the same thing, mirror image of the same thing will happen on the right hand side. And so heat neither can flow from left to right or right to left across the midline. The only way this is possible is that there will be no heat flow across the midline. And that means that the temperature gradient will be zero across the midline. That means for this type of problem, your central line will be an adiabatic line. It will be a surface, adiabatic surface. And this is how you can generate an adiabatic surface, that if you impose the same temperature here and here with this type of situation, then the midline will be that surface corresponding to the midline will be an adiabatic surface. So all these things you can interpret through this. There are further things that you can interpret, is that the further things that you can what are the things you can interpret? Whether the results are correct or not. How do you know? How do you know this is the solution? That means this is a result for T, U. How do you know U is correct or not? We can take three things. One, that how do we get this thing? We get this thing out of the governing equation and taking help of the boundary condition. So the solution must not violate the very basis on which we have got this solution. So it must not violate this governing equation, it must not violate the boundary condition. First thing you should do is to check the dimensional homogeneity. Second thing you should do is that whether this solution satisfies your governing equation. That is very easy to see. If you put x equal to 0 in this, then the whole of this thing T2 minus T1 by L into x becomes 0. X equal to 0, the whole second term vanishes. U becomes equal to T1. That is what is specified in the boundary condition. If you put x equal to L, then this x by L becomes L by L. It becomes T1 plus T2 minus T1. So T1 cancels, U becomes equal to T2. That is what is given in the boundary condition. So if you see that by substituting the value of x on the boundary, left boundary, right boundary, you get a value of u that is different from the initial boundary condition. You should understand there is some mistake in your calculation or in your derivation. So that is how we can cross check. And what is the thing to be cross checked? You should also cross check whether it satisfies the governing equation. If you take a derivative, it will be a constant because it's a linear equation. So du dx will be equal to T2 minus T1 by L. The derivative is a constant. And if you take a double derivative, it will be a derivative of a constant that becomes equal to 0. So d2u dx square will be equal to 0. It satisfies the governing equation also. The question is, in which order you should check this thing? Should you check this thing first or check this thing first? Because it is easier to check, so check this thing first. If there is some fault it is there, you need not to check these things, rest of the things. So it will be easier to check this thing. Check if it is correct, then you check the other boundary condition is correct, then check the satisfaction of the governing equation. So that is how you can check. And if you see dimensionally it is homogeneous, it is satisfying the governing equation, it is satisfying both the boundary condition, that means your solution is correct. So that is how you can check. And same is true over here, same is true over here. One more thing that I'd like to tell, you have class after 2:30. You have class after 2:30 or not?
কোনো সাবসেকশনের কি সেশনাল আছে নাকি?
Okay, let us try to finish as quickly as possible within 2. One more thing that you see is that when, how do you get the resultant solution for t? That is equal to u plus v. That is adding to v. This is the solution for v, the linear one. This is the solution for u. Linear one is the solution for u, and to that you add the local heights for v, and you get a resultant curve. That is the solution for t. Now, if you see this solution, what you see on the right hand wall, the gradient is always negative, it is downward. Okay, because you are adding a linear thing, there is a downward, it is coming downward, and this is also downward. So if you add these two, it will be coming downward. As you increase the value of x, your t comes downward. If t decreases, that means your dt dx is negative, that means heat flux will be positive, the heat will come out. But what you say here is that whatever the slope here is the slope over here, and that has to be so, because if you don't have any heat generation, then where from the heat comes, whatever it enters from the left, the same amount of heat has to come out to the right, because it is under steady state. When the problem you are considering is a steady state problem, that means there is no internal heat accumulation, there is no internal heat depletion, there is no internal heat generation. All these things are not there. So whatever heat goes inside at any cross section, whatever heat comes from the left has to go out from the right. At any layer it is true. So the heat flux at any layer has to be the same. That means the temperature gradient at any layer has to be the same, right from the left to the right. And even at the intermediate x values, if you draw lines, the heat flux across those lines have to be the same, because it is under steady state. So no layer is absorbing any heat, extra heat, no layer is giving up any extra heat from itself. So what will happen? Whatever heat comes from left has to go out through the right. So the heat flux has to be constant all through. That means the temperature gradient has to be constant all through. For a steady state problem that has no internal heat generation and there is only one way for the heat to flow. If there is a one directional heat flow in a problem that is under steady state and no internal heat generation, then the same heat flux has to flow through each layer, and that means the same temperature gradient has to be there at and each layer. That means the temperature variation has to be a linear one, line, because for a line only the temperature gradient remains constant. Now here, so there is a decreasing temperature gradient is negative all through, whereas here what happens on the left hand side, the gradient is positive because heat has to be pumped out. Because when you generate heat internally, it has to be pumped out. Okay, now how do you pump out the heat? If you take a thin layer about the x equal to 0 line, x equal to L by 2 line, if you take a thin layer of some thickness on the left hand side, some thickness on the right hand side, through that layer, how much heat goes out? The half of the heat in that layer comes out through this, half of the heat in the other half of the layer comes out. Now, if you see this layer, some other layer at a far away distance from this central line, more and more heat is generated inside that layer. So more and more heat it is to pump out. So what will happen is that if you move from the central line where there is no heat generated, so the temperature gradient there will be 0. But as you move away from the central line, that layer has to pump out more and more heat. So the temperature gradient has to be more and more by magnitude. So what you see is that the temperature gradient becomes more and more. It becomes more steeper, more steeper. and their magnitudes are same, but their signs are different. And here it is positive, here it is negative. So when you add this temperature gradient with this temperature gradient, that this may be more than this. The rate of increase of this may be more than the rate of decrease of this thing. Then the net graph will be having a rising thing. If it is rising, that means what? That means heat will come out. It may be that the rate of rise of this thing is less than the rate of fall of this thing. Then there will be a net fall in temperature. That means what will happen? Then heat will come inside. So if it is rising upward, it will come out. If it is rising downward, if it is falling downward, it will come in. And if it may so happen that the rate of increase of this thing is equal to the rate of decrease of this thing, then what will happen? Then it will neither go up, it will not go down, but it will be simply a horizontal line initially. At that point, the gradient will be a horizontal one. That means what? Means there is no change of temperature at two different values of x. That means dt dx equal to 0, which means that this surface is adiabatic. When it will happen? When the slope of this becomes equal to the slope of this magnitude wise, but in opposite sign, then you may have an adiabatic surface over here. So all these possibilities are there. The net graph, the resultant graph, can have a rising trend, can have a constant value, or can have a decreasing trend. But here it will be always decreasing. So it will be always coming out to the right hand side, but to the left hand side it may come out, it may go in, or there may be no heat coming in or out. Let me stop with this thing. I have something more to explain that I'll do the next class. Let me take your attendance and then stop.
Sir, I had a question, sir.
বলো, একটু রোল কলটা করে নিলে একটু সময় পাবো, একটু গলাটা একটু বিশ্রাম পেয়ে যাবো নাকি আগে? আচ্ছা ঠিক আছে, কোশ্চেনটা করো, বলো।
Sir, G dot is the rate of internal heat generation.
Per
So
unit
it
volume.
should be essentially at the expense of the internal energy of the wall. So internal energy of the wall may increase or decrease. So why is G dot always positive?
Zero is not positive, it may be negative also.
Sir, then the condition we wrote here that heat flux at right wall. So that may be less than zero also if G dot L by 2 can be negative.
Whatever I have said, if G dot is negative, then it will be the opposite. Okay, first of all. Second thing is that, what is G dot? G dot means evolution of some heat energy. When can it happen? As I said, maybe if it is an electrical conductor and if a current is flowing, then it may generate ohmic heat. That may be a case. Suppose it is a carbon or some kind of a body that is going through some kind of a chemical reaction. And as you know, chemical reactions are associated with evolution of heat or absorption of heat. It may be exothermic reaction, it may be endothermic reaction. And that reaction, if it is occurring throughout the entire volume, then throughout the entire volume, heat may generate or it may be absorbed. When there is an endothermic reaction, that we can treat it as a kind of a negative or heat absorption kind of thing. There, this G dot may be negative. And when this becomes negative, then the whole thing will be opposite of what I am telling. Okay. If you tell this and that, then everything will get jumbled up, confused. So many things I am telling. I can avoid all these things because at times it doesn't help. It may be more. It may be somewhat detrimental also. Let us discuss simple things, and then we can think of complex things. Okay. Any other question? Anybody has any other question? Otherwise, I'll go for the attendance. Roll 50, Rishabh. 50.
Present, sir.
51, Vishnu.
Present, sir.
52, Abhishek.